This topic essentially is very close to the previous one. We will see like in a moment. It's about specifically the CFS wakeup path for our systems, which is ARM big.LITTLE, heterogeneous CPU capacities. I think some of the talks already mentioned specific scheduler problems on those platforms. The next feature and the next family of CPUs is what we call DynamIQ. I will mention also the subtle differences between big.LITTLE and dynamic. And the topic is specifically about load spreading and or packing on last level cache on those systems. So just to remind ourselves what we have on specific ARM big.LITTLE code currently in the CFS scheduler. Obviously we have this energy model, the energy aware scheduling, which used the energy model to do energy aware and performance related scheduling. Don't worry, it's only enabled on asymmetric CPU capacity systems, so that means only enabled on ARM big.LITTLE right now. And this feature is only working if the system is not overutilized. Overutilization right now means that each CPU in the system, the utilization signal of each CPU is not higher than 80% of the capacity of this CPU. But the problem I want to talk about here is not in this path. It's more like what do we do if we are overutilized? So one CPU in the system has more than 80% of utilization. That means energy aware scheduling is not possible, and in the wake-up path we dynamically switch to the normal wake-up path, which is select idle sibling or the slow path. The second big.LITTLE specific part is the wake capacity functionality. It's part of this equation to understand if for wake-ups we want to go wake affine. That means we want to wake up on the set of CPUs which are sharing the last level cache. And
wake affine is basically, do we want to wake to the CPU that woke us up? It's for the first level cache.
okay, yeah. So right. So the current CPU is part of this LLC domain. The current CPU you see here, it would be SMP processor ID, right? So CPU.
There's two affines. There's the affine get domain and wake affine. So like it's mixed into like waking up as like waking CPU and waking up just into the waking CPU's get domain.
So select idle sibling basically voids the difference because it currently searches the entire domain. But Oracle guys would like to not do that.
Okay, but we can agree that this won't affine essentially distinguish or make the decision if we go select idle sibling or we go slow path, which is important for us. This is like a demonstration how now we talk about big.LITTLE specific problems on wake-ups. This is the ideal scheduling on a big.LITTLE system. So you see here we have two scheduling domains, 4 CPUs, 2 littles and 2 big, and they all run, each CPU runs the same kind of task. And obviously what you see here we talked about this before, on the big CPUs, the tasks they finish earlier. And the current code right now, the misfit and also stuff Vincent told us about, wants to make sure that immediately the big CPUs help out the little CPUs so they can finish earlier than when those tasks would have essentially finished on the little CPU. And this specific picture shows you a test case we are in the mobile world we are very concerned about. That's Geekbench. So you have the multi-cluster tests of Geekbench. They run n task on n CPUs, always doing the same kind of work, and a test in Geekbench is subclustered into sections, and so each section does work, and then the task they all wait on a sync to continue with the next subsection. This is how all the tests are essentially laid out. And the issue is that in reality it doesn't show this behavior like I just depicted in the idle case, and so we always have to deal with, at the beginning after a sync event, we have to deal with co-scheduling on the big CPUs, and eventually load balance will spread out those tasks later on when there is load balancing on die level. And so the test cases, they essentially suffer from this kind of behavior in all subsections of each test case. And so why is this? The problem is because all of the tasks, all of the 4 tasks, they finish on a big CPUs, you get the pref CPU bias towards the big CPUs. And if the system is overutilized, and we talk about this wakey flip stuff in a moment, wakey flips and wakeup, which essentially wakeup makes sure that the pref CPU and this CPU, if they don't have enough capacity for the utilization of the task, they would essentially also go into the slow path. This is not happening here because all of them, they went to sleep on a big CPU, so this is not catching this problem. And obviously this problem only exists if we do shed domain on die level. Maybe I have to explain this a little bit. On traditional big.LITTLE, this would be the natural scheduler domain layout. But more recently we have, for instance, on the Snapdragon 845, we have to deal with systems which are so-called DynamIQ systems, where you have one cluster and this cluster shares big and little CPUs within a cluster. So essentially you would only have an MC scheduling group containing all 8 CPUs. But what our customers are doing, because of dependencies towards older version of the energy model, but also to subtle problems we still have in the wakeup path, they introduce so-called phantom domains, where they introduce in their DTs a specific structure which is called CPU mask or CPU map, and in the CPU map you can create virtual shed domains. So we end up having a shed domain, a 2-level shed domain, bigs in one, littles in the others, even though they all share the last level cache.
Sorry, Dietmar, you say that they have created this phantom domain for which reason?
For the energy model in the product, right? Because you remember the energy model in the mainline right now is per CPU, so we don't have energy model information per shed domain cluster. But due to historic reason, in the current Pixel device or maybe the Android devices of 2018, they still have this feature using the old energy model and not the one which is in mainline.
Well, the thing is, also the fast path is kind of broken. You don't have to rationalize at all in the fast path. So if you compose your CPU at the MC level, with the code as it is right now, which is the whatever you want to have that if you wanted to have both CPU at the MC level, you would need this time.
Yeah, so for the product release of last year and this year, it was safer and to go with these phantom domains even on Snapdragon 845. And I just wanted to understand this wakey flip stuff a little bit more, and I just wanted to know why is this not helping in this kind of circumstance. So the patch is from 2013, and somebody tried to argue he was not satisfied with going always select idle sibling, and he mentioned a specific workload which is Geekbench, probably Geekbench. He had that's like a database workload, and he was arguing he gets much better performance if he's not consolidating the load all the time on the LLC. And that's why he introduced something which is this wakey flips, where for a task T1 or T2, we keep a counter which is always incremented when at wake up we understand that, or if we can figure out that the task is woken up by another waker. So this gets incremented, and there's obviously also a way to decrement this. So it's not only increasing, but the condition we have is this one. So T1 and T2 is the CPU we're running on currently, so SMP processor ID, and the task which has to be woken up. And the code makes sure that we know which task has the smaller wakey flip field, and if this smaller wakey flip field is at least bigger than the LLC size is the number of CPUs on last level cache, and so it means it's 4 on a smartphone we have right now in a 4x4 big little system, and the bigger value of the wakey flips is bigger than the wakey flips multiplied by the LLC size, then we would spread the load. But as you can see here, I used the example of a Geekbench multi-core test case, a specific one. You see that those values are not returning 1 for this condition here. So this is not helping, and I mentioned this already, wakeup is also not helping because the task is waking up on a big CPU and the waker runs also on a big CPU. So both of these conditions are not helping to force us into the slow path. I mentioned this synchronization mechanism between those subsections of the test case, and for Geekbench it turns out to be like this p-thread barrier init or p-thread barrier wait actually, where all of those 8 tasks have to go into a p-thread barrier wait, and then they all will be woken up at the same time. So kernel implementation side would be the futex wait wake functionality, and an idea a former colleague of mine, Brandon, played with was to just propagate the length of the wake queue into the system. And yeah, I want to know what people think about this.
There's too many user locks that have their own queues of single tasks. Like if they do any of their own task management on the lock, then you'll always see n single wakes.
Yeah, we would only use this if the number of if the wake queue length is bigger than the LLC size, right?
Yeah, but I'm just saying there's too many implementations of locks that will not give you.
True. That's only the specific p-thread barrier wait stuff, right? So there are others, but so on an Android system 4.9, you can see that based on this read-write semaphores also shows this kind of behavior. And obviously we don't have POSIX or System 5 message queues on Android, but I guess they would show you the same kind of behavior. So the implementation we have for this is pretty simple. The task struct has this number of wakey sibling field. The wake queue, when it's initialized by the user of it, will initialize this count field to 0. When we add somebody to the wake queue, we increment the count. When we wake them up, the task gets this information, and this information of the head count is then propagated into the wake write function. It doesn't have to be wake write, but essentially in the decision point where we say select idle sibling or slow path. And if we hit this condition that the wakey sibling number is bigger than the LLC size, then we return 1. So there was a patch on October 2017. Unfortunately, we didn't push it further back then. How does this look like on our Geekbench test case? I say our test case, but it's essentially the mobile industry which is interested in Geekbench. Like I said before, there are a number of test cases running on single core and multi-core. You can see here's 2 examples of the 2 last single core test cases, mem bandwidth and mem latency, and with the AES crypto test case, that's the first multi-core test case where we have to deal with those subsections. The device is a Pixel 3 Snapdragon. CPU 0 to 3 are little CPUs, 4 and 7 big CPUs. It's a dynamic system, like I said before, and we have those phantom domains in 4.9. In the current Pixel 3 device. When we go into one of the specific test cases, that's 4.9 vanilla kernel, we see that we have those little CPUs not used, whereas when we all wake up after the sync, the p-thread barrier wait, we have co-scheduling on 2 big CPUs. Eventually, the load balance will figure out and will try to migrate at least one task to a little CPUs, but that's the problem Vincent was talking about. And this is actually happening on various subsections of this specific multi-core test case in Geekbench. And with a patch, yeah, obviously, we have a way to propagate this information. And when we wake up those tasks, those 8 tasks, we can do a much better job in the slow path. Vincent, you mentioned this, that sometimes it depends on the state, on the start condition. Maybe that's also something related to this. It doesn't happen all the time, because obviously on a real system you will have other tasks like running with this test case itself. Another thing which we could do to test this, our test application RT-up, which we do most of our big.LITTLE test cases on, has a barrier feature right now, but it's not implementing the pthread barrier wait, but something else where you wake up one thread after the other. So what we could do on the test side is to come up with a barrier default type. There's also a patch still lingering from Brandon, 2 years old or so on this. And I'm not sure, somebody said that we want to implement it like this, that we have a barrier type, and behind the barrier event we can then choose the different way of... Yeah. So, yeah. So this would be a way to test this feature. But the question is do we still need this because of the phantom domains? We would like to get rid of it, etc. The issue is if we would get rid of the phantom domain, so we would clean up the wake-up path, that means we would not need this kind of trick playing with this.
Actually, I'm thinking, people are talking about Brendan's patch. One of the things he had to do, if I remember correctly, was disabling the remote queuing thing that we were actually discussing this morning in
The shed feature, you mean?
Yeah, the shed feature thing.
Yeah.
Because what was happening was you would wake up a class, decide to move it on the legal CPU, and since big.LITTLE CPU with DynamIQ will have to be in different LLCs, you would do the remote queuing, so big.LITTLE CPU would do that with the wake up. But then since all the wake up and the task wake up at the same time, by the time the task actually gets queued in legal CPUs, you're taking decisions to place the other ones. So you don't
Exactly.
see the task
Yeah.
queue.
So
Diagrams for sure, right? Like if you did you would see the little CPU wake up and pick something up. But the choice here was whether you did a remote NQ and IPI or whether you did a remote list add, remote NQ and signal or a remote list add and IPI. In both cases, you'd see them picking up the work. They chose the big CPU to run on. They chose Prev CPU, so there's no remote NQ.
Well, right. What I'm saying is, even if you have a patch that Dietmar is talking about, to actually have the queue length thing and to disable, to force, to go to the slow
What I'm
path.
saying is the same cache choice depends on you already having Prev, like not picking towards Prev CPU. Like they woke on Prev CPU and on for the big. So you can be going through the same cache choice. Because the same cache choice is assuming you're waking them up.
Yeah, exactly. So what Dietmar is doing is, what the patch is talking about is making sure that you actually search the full system so that you will wake up and catch multiple CPUs even though you wake up and big. That's the fix it's suggesting, right?
yeah. So the idea.
What I'm saying is even with that fix, you don't solve everything because of that remote.
Yeah. So the chat feature has to be disabled.
Right.
Otherwise, you don't have the
You
load.
get the wake up though. That's nice. Like,
So I'm not following. What's the problem with the remote wake?
So if you have
they're just talking about the cache range. But that's an efficiency thing, not a problem.
Right.
yeah. So what's the chat feature?
They say they have to disable it, but why?
No, that's what I'm saying. I'm saying that they don't. They shouldn't have to say that. It should just be an efficiency check.
All of the tasks wake up on BCP, right?
Sure.
And then at that point you decide to move some of the tasks on equal CPU.
Moving and wake up is different for that.
The task wake up on BCP, you then decide to wake it up to run it on equal CPU. So
Can I- So that's idle balance, right? Or load balance?
Wake up.
No, wake up balance is before that. Wake up balance is before you get onto the queue.
Yeah, right. So you decide to put it on the system. So at some point you will need to enqueue it, right?
Yes, but if you put it on the big CPU, in what you just described, you already passed that choice.
Right. So what I'm saying is, even if you decide to task or accept the big CPU, you decide to run it on the little CPU, then you have to do that.
So you take the interrupt from the big,
Right.
and you're choosing to place on the little.
Okay, that's what I'm saying. At that point, since big and little CPUs are in different LLCs,
Yeah.
you will do the IPI thing, you enqueue on the little CPU. The remote wake up thing was discussed this morning during the center. And because that takes time, because you need to wake up the little CPU, this is the remote work kind of thing. So all the decisions that you're making on the big side, when you do those decisions, you don't see the task.
They do. They check the idle. Idle CPU checks the others.
No, we go to the slow path.
It's not an IPI.
Idle CPU checks the L list.
Idle CPU, but that's not yet in the load account.
Exactly.
It's not in load accounting, but it depends where you're on the paths.
Yep, exactly. But what we want to do is, like, we want to avoid select idle sibling. We want to go to the slow path, and the slow path needs the load information from the previous task put somewhere. So when it scans the CPU, it sees that this CPU has already a task, and that's why we have to disable.
So what I'm saying is, disabling that thing and this whole thing is a bit of a mess, and I agree with that. All the problems we have come from the fact that we have different, MC levels and 2-level yards, everything like that. We say we have different LLCs for two clusters. But if all of them were in the same domain,
Exactly.
more than the group, then we solve all of those problems, of course.
Yeah. So
Then,
the problem is then we have to be very strict about to tell our customers not to proceed with this phantom domain stuff anymore. And I think there is something to do for us in the wake up, because wake up has no meaning anymore, right? Like okay. So we should follow probably for big little systems or dynamic systems on mainline. We follow the approach to not introduce those phantom domains, because the initial problem is that the same task essentially ends up they get tilted towards the big cluster on those systems, right? So that means we should not care about traditional big little anymore. We should just do based on LLC, shed domains based on LLC. Okay, it's just to lose this LLC feature then on classical big little. Mm-hmm. Okay, because of the hidden dependency towards, once you establish that pref CPU and this CPU is not able to deal with the task, that means you make like a black-white decision, big or little, which we should get rid of. Okay.
I think some of that's a red herring, because like the barrier weight could easily be coming from the same SD. It's not like this CPU and prev CPU don't matter at all. It's that your domain's full and you want to wake it up to another domain.
Mm-hmm.
Everything else is a distraction.
For us, it was hard to understand if like to use information out of the wake system towards scheduling is something where, because you tied those two different subsystems together, it might be not a good idea, even though it gives us this kind of behavior we want. But I think like long term or mid term, we have a better decision to just get rid of the phantom domains and create proper big little scheduling and wake up to deal with different kind of capacity, because it doesn't end in a cluster where we only mix big and little. The next generation will be big, little, and medium, for instance, right? Yeah. Yeah, it's already a reality, I guess. So, yeah, that's all I have. If there are no further questions, that's not the case. Okay.